NASA's Viking project accomplished the first successful robotic landing and detailed scientific study on the surface of Mars, twice. Vikings 1 and 2 were launched from Earth in 1975 and reached Mars in 1976. Each of the two Viking missions had an orbiter spacecraft and a lander spacecraft. The orbiters acted as mothership for their respective lander, encapsulated for protection during launch, cruise, and an initial Mars in-orbit period of about a month. The landers were designed and built by Martin Marietta Aerospace, now part of Lockheed Martin. Both Viking landers 1 and 2 landed safely in July and September 1976 respectively. In order for humanity to learn the results of the lander's imaging and other science investigations and engineering aspects of the lander spacecraft, some means of interplanetary communication was necessary. The landers also needed the ability to receive information from mission controllers on Earth in order to adapt pre-programmed plans to actual circumstances encountered on Mars. Therefore, each Viking lander had specialized radio systems. All of the lander's radio components were designed and built by RCA as subcontractor to Martin Marietta Aerospace, who built the overall lander. Martin Marietta also provided the interface hardware for mating the radio equipment to the lander, parts of which were rather complicated, as will be shown. The lander had two independent radio subsystems. The relay communications equipment, which used a broad pattern antenna to transmit information from the lander to either of the two Viking orbiter spacecraft orbiting approximately once per day around Mars. The chosen orbiter would then relay the information to Earth using the orbiter's relatively powerful radio system. The lander's relay radio transmitted at 381 MHz in the ultra-high frequency or UHF region of the spectrum. The lander's second radio subsystem was the direct communications system, which could both transmit and receive information directly to and from Earth. There were two S-band antennas, a broad pattern low-gain antenna which could only receive from Earth, and a steerable high-gain antenna which could transmit and receive directly to and from Earth. This subsystem operated in the S-band region of the spectrum, receiving on 2113 MHz and transmitting on 2290 MHz. All of the radio electronics components were built by RCA's Astro Electronics division and were located within the lander. For the UHF Relay communications equipment, this included a transmitter. The S-band direct communication system had a number of components. Two transponders, which performed S-band radio frequency or RF reception and generation of the RF transmission signal using a modulator exciter unit. Two traveling wave tube amplifiers, which provided power amplification of the transponder output as needed for transmission by the high-gain antenna. A microwave components assembly, which handled RF filtering and splitting of radio signals and switched the output of either traveling wave tube amplifier to the high-gain antenna. A command and control unit, which handled command detection and decoding and interfacing with other components, including the lander's computer, and controlled the high-gain antenna steerable drive mechanism. The three antennas were built by RCA's Missile and Surface Radar division. This video uses a work-in-progress, high-fidelity digital 3D model of the lander to show mechanical aspects of the antennas. The antenna used for a given communications pass depended on various factors, including phase of the mission, orbiter and Earth ground station scheduling, electric power available on the lander, and quantity of data to be broadcast. The first lander antenna to be used on landing day was the UHF Relay Antenna. It was activated just before the lander capsule separated from its orbiter. Engineering and science data from the lander and from instruments mounted within the aeroshell to study the Martian upper atmosphere during descent were continuously transmitted to the orbiter, which transmitted it to Earth in real time. The data were also stored on the orbiter's tape recorder, which proved critical for Viking 2 when its orbiter lost communications lock on Earth during descent and landing. After orbiter recovery a few hours later, the stored Lander 2 data were successfully sent to Earth. The UHF antenna design featured two superimposed turnstiles over a tuned 3-wire grid ground plane. The arms of each turnstile emitted the radio frequency signal. The lengths and angles of the arms produced an approximately hemispherical radiating pattern. A broad pattern was necessary for the transmitted signal to reach the Viking orbiter without requiring accurate lander orientation, such as during Mars' atmospheric entry and shortly after landing as the orbiter passed high overhead. The open grid ground plane reflected the RF signal to increase its upward strength. Grid spacing was chosen based on the UHF wavelength of the emitted RF signal. The antenna central housing had 4 slots cut into it, which helped the antenna generate the exact desired RF frequency. Small tabs at the bottom of each slot allowed fine adjustment of the antenna characteristics. The slots were filled with insulating dielectric rods to increase the usable transmitter power, selectable between 1, 10, and 30 watts, without causing electric arcing across the gap. The rods also prevented entry of Mars dust. Each arm terminated in a large metal ball. These prevented damaging corona discharge arcs from occurring at the arm tips, which are prone to occur in low-pressure carbon dioxide environments such as the Martian upper atmosphere. The corona balls were enclosed in polyurethane foam with fiberglass covers. The photograph shows an unpainted test antenna. Perhaps the most notable use of the UHF antenna was to transmit the first image ever taken on the surface of Mars, July 20, 1976. The image was captured and sent by Viking Lander 1 during the first few minutes after landing. Orbiter 1 relayed the image data to Earth in real time as it was being received from the lander. The S-band low-gain antenna, or LGA, was designed to receive new spacecraft commands from Earth and store them into the lander's computer memory. In order to be as flexible as possible, the LGA reception pattern was essentially the hemisphere above the lander, so that if Earth was visible in the Mars sky, then the lander could receive a signal regardless of the lander's tilt or compass orientation. The LGA had the same basic double turnstile over 3-wire ground plane reflector design as the UHF antenna, scaled smaller to account for the S-band's higher radio frequency and thus shorter wavelength compared to the UHF band. The LGA did not need any protection from corona arcing at the turnstile arm tips because the LGA did not transmit and thus did not have high power applied to the arms. Within a cylindrical fiberglass phenolic radome, the LGA's housing retains the 4-slot configuration of the UHF antenna. The photograph is of an unpainted test unit. The capped coaxial cable connector on the side of the LGA base was used during pre-launch antenna testing. The most complex of the Viking lander's 3 communications antennas was the S-band high-gain antenna, or HGA. In order to transmit a signal across hundreds of millions of miles that could be picked up on Earth, even by the huge and extremely sensitive receivers of NASA's Deep Space Network, the HGA needed to concentrate its 40-watt maximum RF power within a fairly narrow cone pattern pointed at Earth. This was accomplished by the HGA's 30-inch diameter parabolic dish reflector. The term high gain refers to effective amplification of the emitted radio signal by focusing its energy in the direction to which the dish points. The dish needed to be located as high as possible for best line of sight from the lander to Earth when above the local Mars horizon, in order to minimize obstructions from other lander components. Meeting this clearance requirement was challenging due to the limited volume available within the protective shell in which the lander was encapsulated until shortly before landing on Mars. As a result, the RCA-built antenna was mounted on a hinged deployment mechanism built by Martin Marietta. The HGA mast was stowed or folded down during launch from Earth, cruise to Mars, and landing on the surface. Antenna mast rotation was precisely limited both when stowed and deployed by pins installed in the mechanism's elbow and stop shoulders integrally machined into the hub. The deployment mechanism's support tube and hub were vented via a filtered opening on the bottom of the base plate. This allowed the mechanism to cope with a range of atmospheric conditions, from Earth sea level pressure to the vacuum of space during cruise to Mars, to the low-pressure surface atmosphere on Mars. The filter prevented any Martian dust from entering the deployment mechanism and possibly jamming its bearings. A downlock mechanism held the stowed antenna in place securely, both to prevent inadvertent deployment and to stabilize the antenna during the strong vibrations of Earth launch, Mars atmosphere hypersonic entry, and landing. When manually stowed before launch, the HGA's drive head fitted between the two arms of the downlock. A tab on each arm engaged slots in the blue stabilizer fittings attached to the drive head. The antenna was locked in place by a pyrotechnic pin puller device mounted on the downlock. Before launch, the HGA dish was rotated to align a tab on the back of the dish mounting frame within a clevis built into the drive head. A sturdy pin or rod extended from the pin puller and passed through clevis and tab. The pin thus locked down the HGA's folded mast and also kept the dish fixed in its minimum volume configuration. Within the pin puller, a small shear pin prevented the main pin from retracting inadvertently. A few seconds after landing on Mars, the HGA was released by firing the downlock pin puller. The pin puller was actuated by two redundant Viking standard initiators, or VSIs. An electric current ignited a very small zirconium potassium perchlorate explosive charge within each VSI. The resulting rapid combustion generated a high-pressure pulse of gas which was expelled from the VSIs into a small chamber within the pin puller. The expanding gas pushed on the underside of the pin's flanged head with sufficient pressure to break the small shear pin. The main pin then rapidly retracted into the pin puller body. A deformable shock absorber cap slammed into the end of the pin puller and deliberately jammed the fully retracted pin, preventing rebound. With the pin withdrawn from the clevis, a torsion spring on the downlock pivot axle rotated the downlock arms slightly away from the HGA drive head, disengaging the stabilizer tabs. That entire release process occurred in only a fraction of a second. The high-gain antenna mast was then free to deploy. The mast was raised by a pair of constant force springs. The two roll-up power spring assemblies, each with 9 cobalt chromium nickel alloy laminations, provided 400 inch-pounds of torque. With one end of the springs anchored to the deployment mechanism's hub, the powerful curl-up or roll-up force exerted a pull on spools attached to the rotating elbow. The freewheeling spools reduced friction at the point of spring contact. As the springs returned to their natural, tightly curled state, the elbow was pulled upright, which raised the attached antenna. The power spring's curl action was strong enough, if unimpeded, to raise the 6-pound in Mars gravity antenna fairly quickly, especially if the wind was helping to push the antenna dish. A potentially damaging shock could occur when reaching the upper stop limit. To prevent this, an anchor-recoil escapement governor limited the rate of mast elevation. The deployment mechanism's rotating elbow was connected to a sturdy axle within the hub. The axle and simplified bearings are tinted green to denote that the geometry is approximate. I lack references for the actual shapes. The axle drives a 300-to-1 gear train. The 3D model's green gearbox shape is speculative, but the gear train itself is accurate. The final stage of the gear train drives a 24-tooth escapement wheel through a simple ratchet clutch, which is engaged during deployment. A rocking pallet prevents unrestricted or runaway rotation of the escapement wheel. A cylindrical torsion or rotating pendulum is connected to the pallet, which adds rotational inertia to slow down the pallet's rocking action. Even with the torsion pendulum, the escapement operates very rapidly. The motion is slowed down by 20 times here to more easily see the rocking action of the pallet and the interrupted rotation of the escapement wheel. The ratchet clutch mentioned previously allowed the governor mechanism to be bypassed while the antenna was stowed a number of times during testing and one final time before flight. This was important because the escapement was only designed to be driven in the forward direction. When the antenna and deployment mechanism were manually rotated down, as seen here, the elbow and axle drove the gear train in reverse. That caused the teeth of the spring-loaded outboard half of the ratchet, which was directly driven by the final stage of the gear train, to skip over the inboard ratchet teeth that were machined as part of the escapement wheel. The escapement and pallet, therefore, could remain stationary during antenna stowage. To prevent the antenna from pivoting back down due to a mechanical failure or stronger than predicted wind gust, a ratchet uplock mechanism was used. After a few minutes of rate-limited rotation, the high-gain antenna was fully raised, locked, and ready for use. The most prominent feature of the HGA was the parabolic dish reflector. To reduce weight, the dish was formed from thin front and back skins with an expanded foil filler for stiffness. The radio frequency or RF signal was emitted and detected through a tapered double helix feed winding at the dish focus. The test antenna seen in the photograph is unpainted, which more clearly reveals the feed helix. At the front of the feed was a perforated cylindrical ground plane. This increased the antenna's effective power by reflecting radio waves to or from the feed. The perforations reduced weight and buildup of Mars dust without impacting RF behavior. The HGA sensitivity was highly directional and therefore needed to accurately point toward Earth. Continuous Earth tracking during antenna use was performed by a steerable drive head. The motion seen here is accelerated for clarity. Electric stepper motors rotated the antenna dish in azimuth, or side to side, and elevation, or up and down. Position resolvers on each axis provided feedback to the control circuitry to detect and correct actual versus commanded pointing direction. The RF signal was passed through a coupler within the dish mounting frame and then via a coaxial cable into the drive head. A non-contacting rotary choke enabled the drive head to rotate without twisting the coax cable. Another segment of coax cable then carried the signal out the bottom of the stationary antenna mast. An array of electrical control, power, and ground wires, along with a small coax cable which allowed sampling of the RF signal during pre-launch testing, were routed under a shield on the outside of the mast. Within the drive head, the wires had sufficient slack to be able to wrap twice around the drive head azimuth axis. The high-gain antenna on Viking Lander 1 enabled it to continue operating on its own after the two Viking orbiters reached their end of life and were shut down, 1978 for Orbiter 2 and 1980 for Orbiter 1. Viking Lander 2 reached its end of life in April 1980 after 3.5 years operating on Mars. Lander 2's rechargeable batteries, which were powered by plutonium-fueled radioisotope thermoelectric generators, had failed. Operation of Lander 1, the last surviving Viking spacecraft, ended in November 1982 after 6 years operating on Mars due to a mistake involving its high-gain antenna and batteries. The nickel-cadmium batteries on both landers had experienced gradual loss of charge-holding ability, as do rechargeable batteries to this day. Occasionally, new software was uploaded to each lander's computer with a revised charge-discharge program. These procedures extended the battery's useful life as operational experience was gained. On November 19, 1982, a new battery program was uplinked to Viking 1. Unfortunately, the reprogramming instructions inadvertently commanded the lander computer to store this program into the wrong portion of memory. Rather than replacing the previous battery control program, it overwrote the high-gain antenna pointing program. Unbeknownst to the Viking team members, the antenna had just been commanded to point in an unknown direction by an inappropriate algorithm. After the uplink was complete, normal attempts were made to acquire the typical downlink response from the lander. These attempts failed, and a spacecraft emergency was declared the next day. Ordinarily, the omnidirectional low-gain antenna could have been used to receive a re-uplink of the antenna pointing program. However, the LGA could only use the lander's transponder 1, and its receiver had failed earlier in the mission. The HGA was using the remaining transponder 2, but the HGA was now pointing where? Extensive diagnostic efforts were carried out with identical hardware on Earth. Repeated attempts were made to transmit new instructions to and listen for signals from the lander when, during the next few months, the ever-changing solar system geometry yielded potential alignment between Earth and where the antenna on Mars was hypothesized to be pointing. Despite all this, communication was never restored. The incredibly informative Viking mission, humanity's first study on the surface of Mars, was declared ended in March 1983. I am grateful to a number of organizations for allowing me to conduct research on the Viking artifacts they have preserved. Special thanks to the Viking Mars Mission's Education and Preservation Project, who granted me many hours of access for measuring and photographing a high-gain antenna in their collection. This included use of an endoscopic camera for recording close-up imagery within the confined volumes of the hardware. Thanks also to the Museum of Flight in Seattle, Washington, the California Science Center in Los Angeles, California, the Virginia Air and Space Center in Hampton, Virginia, NASA's Langley Research Center, also in Hampton, Virginia, the Smithsonian National Air and Space Museum in Washington, D.C. Thank you to all.